What's up, guys, and welcome to this video walkthrough on question 5 of the 2016 supplementary exam. It's called Accidents Happen, but it's mostly, let's say, on momentum, impulse. Let's see, there's a bit of work and energy. Let's see what else I can see. Yeah, so that's, I'd say work, energy. Okay, so those are the sections that this question will probably cover. Okay, so let's get into it. Question 5. A truck of mass 2,500 kilograms was being driven at a velocity of 25 meters per second. Unfortunately, the driver did not see the low overhead bridge and drove straight into the bridge, peeling open the top of the truck. The truck was stopped at a distance of, so the distance is 1.8 meters. Okay, so let's actually write out the important information I found. So velocity equals 25 and mass is equal to 2,500. Okay, so yeah, okay, so question 5.1.1. Calculate the magnitude of the change in momentum of the truck during the accident. Okay, so we're looking for change in P, or change in momentum, which is equal to our mass times the change in velocity. Okay, which is equal to our mass, which was 2,500, times the change in velocity. Let's write this as this: velocity final minus velocity initial. Okay, so this truck is stopped, right? So the velocity final is 0, and the velocity initial was 25. So our change in P comes to minus 62,500 kilograms meters per second. Okay, but we want, okay, so the negative sign, because we just want the magnitude, we just care about change in P equals 62,500 kilograms meters per second. Okay, and we don't care about a direction either, because we just care about the magnitude, and we get ourselves 3 marks. Cool stuff. Question 5.1.2, state the work energy theorem. Okay, so it's a definition. Okay, and the definition goes that the work done by a net force on an object is equal to the change in kinetic energy of the object. So basically from this definition, we get that work net, which is also equal to F net change in S, is equal to change in EK. Okay, cool stuff. And we get 2 marks of the definition. Question 5.1.3. Now it says use the work energy theorem to calculate the average resultant force, okay, that brought the truck to a rest. Okay, so we're looking for F net in this question. So the question is, what is F net? Okay, so let's use the work energy theorem. So F net change in S is equal to change in EK. So we can say that F net change in S is equal to a half times the mass times the velocity final squared minus the velocity initial squared. Okay, so what we're going to get is that F net times our change in S is going to be 1.8 meters. Okay, is equal to a half times the mass, which was 2,500 kilograms, times 0 squared minus 25 squared. Okay, and the only unknown here is F net, so we can solve this equation. F net is equal to minus 434,027, so 34,027,78 newtons. Okay, so the minus just indicates the direction, right? So we can say that F net is equal to 434,027,78 newtons in in the opposite direction of the initial motion. Okay, so that just explains to us that the net force is backwards, okay, if that makes sense. And we get 4 marks there. Okay, so question 5.1.4 says use your answer from 5.1.1 and 5.1.3 to calculate how long it took the truck to come to rest. Okay, so how long? Okay, so let's go to our formula sheet. Okay, we're looking at the momentum section. Okay, we calculated the F net and we know what change in P is, so we can use the first row second column equation. F net is equal to change in P over change in T. Okay, so if we use that as our governing equation, we get F net is equal to change in P over change in T, because we want the time. How long is time? Okay, so we can change the equation to change in T is equal to change in P over F net is equal to, okay, I'm going to use the magnitudes only because both of them have negative signs in them, so it's going to be 62,500 divided by 434,027.78. Okay, and change in T is, as we can see, the only unknown, so the time taken is going to be equal to 0.14 units of seconds. Okay, and that's the final answer. Okay, so then question 5.1.5. Fortunately, the driver who was wearing a seatbelt was not injured during the accident. Explain why the driver would have been more seriously hurt if the same truck had stopped almost instantaneously. Use relevant formula to explain. Okay, so the formula I'm going to use is the one we just had, which was F net change in T is equal to change in momentum. Okay, and it says explain why if the change in time was less. Okay, so I'm actually going to write it the way I had it. Okay, that's equal to change in P over change in T. Okay, and we know change in P is the same for both cases. Okay, so for both cases, if the change in T went down, then the F net experienced, so the net force experienced, goes up, which would result in him being more severely injured. Okay, so he experiences a bigger force, meaning the injuries would have been greater. Cool, and we get 4 marks for that. Cool stuff. Let's move on to question 5.2. So a small car of mass 1084 kilograms was traveling east. Okay, so that direction is east at 33 meters per second. A large SUV of that mass was traveling west with that velocity. Okay, the two vehicles collide with each other head on. Immediately after the collision, the small vehicle was moving west. So after the collision, I'm going to do an orange. So the small vehicle was moving west at 5 meters per second. Okay, so after, and everything below is before. Okay, cool stuff. 5.2.1. Name the law you would use to calculate the velocity of the SUV immediately after the collision. Okay, so I would say that it is the law of conservation of linear momentum. So law of conservation of linear momentum. Okay, and the reason is, if we go to our formula sheet once again, let's see which law is that. Is it on here actually? Okay, yeah, so the conservation of, okay, it's not here directly, but if we look at force and momentum, it would be the third equation in the first column. Change in P equals mv minus mu. Okay, so indirectly that is what I'm referring to. Okay, and we get 2 marks. Okay, 5.2.2 says determine it. Okay, so what I'm going to say is change in P. Okay, so let's say change in P, or let's even say P. So the momentum total before is equal to the momentum total after. Okay, so let's work out the total momentum, and I'm going to take east as positive. The east direction is going to be positive. Okay, so momentum is made up of mass of the car, velocity of the car, plus mass of the SUV, velocity of the SUV before is equal to mass of the car, velocity of the car plus mass of the SUV, velocity of the SUV after. Okay, so let's go for inserting some values. So we have 1084 times the velocity of the car is 33, plus the mass of the SUV is 3437 times the velocity. Remember, this is west, so this is a negative. So minus 28 is equal to the mass of the car once again times the velocity of the car after the collision, which was 5 meters per second west, so we have a negative once again, plus the mass of the SUV, 3437, that 3 looks weird, 3437, times the velocity of the SUV final. Okay, so if we look at this equation, the only unknown is the velocity of the SUV, so we can calculate that V is equal to minus 16,02 meters per second. Okay, the minus is an indication of direction, so the velocity is equal to, we took east as positive, so the negative of that would be meters per second in the westward direction. Okay, and we get 5 marks of that. Quite nice. Okay, and we have once again another definition, 5.2.3, define elastic collision. Okay, so the definition of elastic collision is a collision in which both momentum and kinetic energy is conserved. Okay, both momentum and kinetic energy must be conserved. The most important part is that kinetic energy part. Okay, so we get 2 marks for the definition. Use a calculation to determine if the collision was elastic. Okay, so we know that momentum is always conserved. So the question is the kinetic energy conserved? 5.2, my pen's not working. Let's see if I can get it to work. Let's close that. Okay, sorry about that. Let's see if it's working again. Okay, so 5.2.4, there we go. We're looking for EK before the collision is going to be equal to 1/2 times the mass times the velocity of the cars squared plus 1/2 times the mass of the SUV times the velocity of the SUV squared is equal to 1/2 times the mass of the car was 1084 times the velocity of 33 squared plus 1/2 times the mass of the SUV was 3437 times the velocity. Okay, because the velocity is squared, I can just put the magnitude, because minus 28 squared is equal to 28 squared. So I'm just going to put the positive. Okay, and if we crunch those numbers, we get EK before is equal to 1,937,542 joules. Okay, no units, it is a scalar. Okay, now we just need to get EK after, which is also equal to 1/2 mass of the car, velocity of the car squared plus 1/2 times the mass of the SUV, velocity of the SUV squared, but this is always after the collision. So what we have is 1/2 times the mass, 1084 times the velocity. Okay, again, I don't care about the direction, so 5 squared plus 1/2 times the mass, which was 3437 0.37, and the velocity, which we calculated as 16.02 squared. Okay, so EK after is equal to 454,587 units of joules once again. Okay, so what we can say is that EK before not equal to EK after, therefore inelastic. Okay, because or inelastic collision as kinetic energy not conserved. Okay, so if in a different question we get EK before equals EK after, then it would be an elastic collision. But that's not the case here. Okay, cool stuff. And that's the question. 30 marks. Nice big question, lots of marks. Not too difficult, very straightforward, as long as you know your definitions and your laws. Let's see, there were 1, 2, 3, 4, 5, 6 marks in the definition. So yeah, in the definitions section. So that's quite nice. Okay, cool stuff, guys. Yeah, that's the end of this video. Thanks for watching. I hope you found it useful, and I have been concerned about time. 17 minutes or roughly around that time for 30 marks is not bad at all. Okay, thanks for watching, guys, and cheers.